Hey everyone, so in this video I'll be explaining, talking about the dot product, what it is, but also thinking about its significance and why we define it the way we do. So when you're first introduced to vectors, usually the first operations you talk about is adding vectors together, and subtracting vectors, and doing things like that. Now, dot product is an operation on vectors, just like addition and subtraction is, but it's slightly different. And what makes it different is when you add vectors together, if you take a vector and add it with another vector, the result is you will get some other vector, right? You will get something with a direction and a magnitude, and that's the same if you subtract. But when you do the dot product of two vectors, the result is actually not a vector. So if I take two vectors and I dot product them, what I get is not a vector, but just a singular number, like a number like 1, 2, or 3, or so on. And this is pretty different. And so the basic question is what is so important about this number? What does this possibly tell us about these vectors? So usually when students learn this, they're first introduced to this definition of the dot product. So if we have two vectors, vector x and vector y, the dot product of these two vectors is basically you take the first component in this vector, times it with this, and then you add this component times with this. So x1 times y1, x1 times y1 plus x2 times y2. This is the usual definition you first are introduced to. So just as a quick example, if we have the vector 2, 6, dot product with 1, 3, we just times 2 and 1 plus 6 and 3. And so in this case, it would be 20. And so yeah, the idea is you take two vectors, you apply this operation, and you get a number out. And a very, very natural question is so why are we defining it with this weird rule? Because in some sense, we're defining a multiplication on vectors. And it would make sense to define it a whole lot of other ways. I remember when I first learned it, I thought, why don't we just times these and get another vector, x1, y1 times x2, y2. So the question is, why did we define it this way? And what is so important about this number 20 in this case? And so that leads naturally to this question of, why is it defined like this? But it also introduces a second definition. So sometimes this is called the geometric definition of the dot product. So you hopefully have seen something like this. So you can take the dot product, if you have the components of the vectors, you can take it and then get the number quite easily like this. The other way a dot product is defined is the dot product of x and y is equal to the modulus of x times the modulus of y and times by cos theta, where theta is the angle in between x and y. So as a quick, maybe a drawing just to help, if we have our vector x and our vector y, this is the angle theta. And so this is saying you can take the dot product by just taking the length of this vector and the length of this vector, multiplying them by each other, and also multiplying it by cos theta. Now, in my opinion, I think this definition should be taught first, because with this definition, we can actually understand what is so important about this number that's associated with the dot product. And that's because this has a very specific meaning and a very nice intuition. So what we're doing here is, and I might just rearrange this so it's sort of even easier to see, x cos theta times y. So this vector has length x, right? Has length x, and this vector has length y. And so x cos theta is actually just equal to this length here. This length here has length x cos theta. Reason being is this is a 90-degree triangle, and so cos theta equals to adjacent divided by hypotenuse, and so the adjacent side is just equal to x cos theta. And so specifically, this length is sort of the magnitude of this vector that's in the same direction as the vector y. And so actually what we're doing with the dot product is we're taking two vectors and we're considering the component of this vector that's in the same direction, where they're in the same direction, and we're just multiplying those magnitudes. So we're multiplying x cos theta and y. And so this has a very nice sort of physical or geometric significance. You can, maybe one example for those that study physics is, in physics there's this concept of work, and work is just how much force you apply times the distance that you apply it on. And so the usual example is like you have a box and let's say you're pulling it with some force. You take the newtons, the amount of force you're applying, and the distance that you apply it over, and you just multiply these quantities. But things get a bit tricky if, let's say, I'm applying this force on an angle. Imagine I'm pulling this box with like a rope at this angle. In this case, although I'm pulling it with some amount of newtons in this direction, I'm only concerned about the component of force in this direction, right? And what is the component of force in this direction? It'll be equal to F cos theta. And so work actually equals force times displacement or distance cos theta. Because we have these two vectors, but we only care about when they're in the same direction. So we take the magnitude or the component of the magnitude in the same direction, and we just multiply these magnitudes. And so thinking of it like this, it makes a lot more sense why the dot product is kind of a multiplication. All we're doing is we're multiplying the magnitudes of two vectors, but we also have to correct for the fact they're pointing in different directions. If in fact the directions are the same, if they're just two vectors of the same direction, it's literally just multiplying those two vectors. And so if we go back to this example here, actually I picked two vectors that are in the same direction. So we can actually recalculate this dot product simply by taking the magnitude of this vector and the magnitude of this vector. So magnitude of 2, 6 equals to root 4, equals to root 4 plus 36, so equals to root 40, and magnitude of this vector equals to root 1 plus 9, so equals to root 10. And so if you times these together, the dot product is equal to root 40 times root 10, which equals to root 400, which equals to 20. And so really what the dot product is doing in this case is simply multiplying the magnitudes of these two vectors, and that has a very nice and intuitive meaning. Cool. So the only remaining question is, why is this definition equivalent to this definition? Because that's definitely not clear. And so I'll finish this off by a short proof of exactly that. Why are these definitions equal? Cool. So let's draw our diagram again. We have a vector y, some vector x, and let's also fill in this and give this vector, the name Z. So this is just a triangle. Let's call this theta. And any triangle, it doesn't have to be a right angle triangle. We can use the cosine rule. The cosine rule will relate the side lengths with this angle theta. So if you remember that formula, it's just that this length squared equals to x squared plus y squared minus 2xy cos theta. This is just the cosine rule. And applied to these side lengths, keeping in mind that these are actually vectors. Cool. So this is one way we can sort of express the side length of this squared. But as I said, these are vectors, and so we can actually express this side length a different way, because we know that z simply equals y minus x, because vector y plus vector z equals vector x. So if y plus z equals x, yeah, you can just bring the x to the other side, and we get z equals y minus x. Now, this is just equal, if we give these vectors names, this is just y1 minus x1, y2 minus x2. And so the modulus of z squared is just equal to z1 squared plus z2 squared, right? Here I'm just calling z1 and z2. But we know what z1 and z2 is, right? We know this is z1 and this is z2. So this equals to y1 minus, x1 squared plus y2 minus x2 squared. And expanding this, we have y1 squared minus 2 y1 x1 plus x1 squared plus y2 squared minus 2y2 x2 plus x2 squared. Now just rearranging these terms, we have y1 squared plus y2 squared, right? This and this. We have x1 squared plus x2 squared. And lastly, we have these terms, minus y1 x1 minus y2 x2. So minus 2 y1 x1 plus y2 x2. Cool. Now, this is just the expanded form of the modulus of vector y, right? The modulus of vector y is just, modulus of vector y squared is just y1 squared plus y2 squared. And so we can write this as just modulus of vector y squared plus this squared. And now we just are left with this, y1, I might just x1, y1 plus x2, y2. Cool, so that was a bit of work, but you might be able to see the point, because now we have two expressions for the modulus of z squared. And to make it super obvious, let me bring him down here. And they are identical. And so if these two expressions are the same, and sort of these whole terms are the same, right? That tells us that these parts of the equation must be equal to each other. So specifically, it tells us that this weird expression x1, y1 plus x2, y2 is actually just equal to the modulus of x, y, cos theta. And so it doesn't matter which one you call it, both of these are just equal to, or it doesn't matter which way you define it, both of these are the same, and so both are the dot product of x, y.